Hello everybody and welcome to a new problem from the strings chapter. This problem is called string matching and it is a fundamental problem that is going to introduce us to two new algorithms that everyone should know when dealing with strings. Let's read the statement together. We are given two strings consisting of letters and we should find every occurrence of the second string as a substring in the first one. So in this example we have the text string, which as you can see is the larger one, and we have the pattern string, and we have to find where this string appears as a substring in the first one. As you can see here, the answer is an array consisting of two indices, 5 and 7. And that is because the substring ABA first occurs here in the text substring, ABA, 0, 1, 2, 3, 4, 5. So the start index is 5, and then it appears here, ABA, and the start index here is 7. And this is why we return 5 and 7. Awesome. Now, coming up with a brute force approach for this problem is super simple. All we need to do is check each and every substring of length equal to the length of the pattern string and compare the substring to the pattern string. And if they are equal, just push the starting index into our answer array, which we are going to return in the end. And this is how the code will look like for the brute force approach. We have the array answer, which is initially empty, and we will denote the length of the text string by n and the length of the pattern string by m. And we are going to try out each and every substring in text of length m. So all we need to do is just set the starting index of that substring, which can be between 0 and n minus m, and then check if the substring text from I to I plus m minus 1 is the same with the pattern string, and if so, we are going to push the index in the answer array and of course in the end return the answer. What is the time complexity of this algorithm? Well, this is constant. These two are of course constants. We have a for loop which does a total of n minus m plus 1 iterations, and then we check if two strings are the same. You can do this with syntactic sugar, a built-in function, or even by yourself. You can write a function in which you make a for loop and basically check if each two corresponding characters are equal. It doesn't matter. It is super simple. We know how to do that. And the time complexity of this is going to be equal, of course, to the length of the strings, which is m. So we are going to do n iterations here. No matter what, be very careful. Even if you call the built-in function, that is not going to be constant time, right? And if so, this is constant, pushing an element into an array, and then return an array of size at most n minus m plus 1. So this is also going to be n minus m plus 1, okay, because you have to copy all those values. Doesn't matter. The point here is that this here is constant, n minus m crossed m, constant. So this piece of code is big O of n minus m crossed m. All right. And of course, this here is also big O of n minus m. And the final time complexity is going to be the greatest between these three, which is of course this one. So our brute force approach is big O of n minus m crossed m. Now, this is obviously not very quick. If let's say both strings have a length of at most 1 million or 100,000, it's going to be super slow. So we need to come up with a better approach. As you can see here, the time complexity is given by the fact that we first try out each and every substring of length m. So this is the first stage of the brute force approach. And the second stage is comparing two strings of length m. So in order to come up with a brute force approach, of course, we are going to optimize one of those. And we will start by optimizing this. And this is where we are going to introduce the Rabin-Karp algorithm. All right, what is the Rabin-Karp algorithm? It is a string searching algorithm created by Michael Rabin and Richard Karp that uses hashing to find the occurrences of one string in another. Now the natural question is, what is hashing? Hashing is the transformation of a string of characters into a usually shorter fixed length value or key that represents the original string. Hashing is often used to index and retrieve items in a database or in a collection because it is faster to find the item using the shorter hashed key than to find it using the original value. What we usually do, and what it is also done in the Rabin-Karp algorithm, is hashing a string to an integer. if for each string we can find a unique integer that is going to represent that string, then comparing two strings will be a lot easier. S1 equals S2 if and only if the hash value of S1 equals the hash value of S2. As you can see here, comparing two strings is big O of L, where L is the length of the strings. While comparing the hash values of these two strings, which are integers, is going to be performed in big O of 1, right? Comparing two integers takes constant time. So all we need to do is come up with the function hash, which given a string argument is going to return an integer. And also this function should make sure that the hash values of two distinct strings are indeed going to be distinct. And the most common way of doing this is using polynomials. In order to build these polynomials, we choose a constant number x, which is going to be usually a prime number. And for each string of length n, which looks like this, S0, S1, and so on and so forth, Sn minus 1, the hash value of s, or the polynomial associated to this, is the value of the first character, which note it is going to be the ASCII code of it, crossed x to the power n minus 1, plus the second character, the ASCII code of it, crossed x to the power n minus 2, and so on and so forth, s of n minus 2 crossed x, plus the last character s of n minus 1. As you can see, we are computing a sum consisting of the ASCII code of each character multiplied by x to the power of how many characters there are on its right. And let's take an example to understand this better. For example, if we choose x equals 13, which is a prime number, and the string s equals abc, then the hash value of abc is going to be the ASCII code of character a, which is 97, crossed 13 to the power of 2, plus the ASCII code of b, 98 cross 13, plus 99. If we compute this formula, we are going to end up with the value 17,766. It's easy to notice that for a string different than ABC, we are going to obtain a different hash value. For example, if we have ABZ, the difference here is that instead of 99, we are going to have 125 or 24, I think. So definitely the value is different. Or if we have ACC, instead of 98 cross 14, we will have 99 cross 14. So definitely we get a different value. The only problem here is that the values of these polynomials are going to be huge. For example, for a string of length only 3, we get a value of 17,766. So imagine what's going to be the value of this polynomial for a string of length 100,000. Even if we pick something like x equals 2, we will still have 2 to the power of 100,000. So in order to make sure that the hash value of some string can be stored in an integer, we have to do one more thing. And that thing is to actually compute the value of the polynomial modulo something. So I'm going to write here modulo mod, where mod is another constant that we are going to choose, and it will be usually prime. Now, everything is okay, and we can hash each string to an integer, but another problem occurs. And that problem is that when we compute the value of the polynomial and then only take the remainder of this value modulo mod, we are going to end up always with a value less than mod. And think about it. When the value of the hash of some string is always in the range 0 mod minus 1, then it is very probable that we are going to find two strings that are different but will share the same hash value. For example, if we pick mod equals 13, think about it. All the hash values are going to be between 0 and 12. So we are only going to have 13 different values. And if we try to hash, let's say, a total of 10,000 strings, there is going to be a huge possibility that two different strings will share the same hash value. And we definitely don't want that. This is called a collision, and it is the only downside of hashing the strings. This is why we usually pick the value of module to be pretty huge and also prime. So for example, a value of modulo that I often use is 10 to the power of 9 plus 7. This is a prime number, and it is so big that we'll reduce the probability of having collisions. For example, in the previous problem, if the text string has a length of 100,000 and we try out at most 100,000 substrings, 100,000 strings will give us 100,000 hash values. So the probability of having two strings or substrings, let's say S1 and S2, which are different, but their hash values are equal, it will be pretty small. But what I want you to remember is that there is always a probability greater than 0 to have collisions. This is why the Rabin-Karp algorithm is a heuristic and doesn't assure us that we will always find the correct solution, but it behaves very well in practice because it is pretty hard to find an input string where you will have collisions. It is very important to have this discussion with the interviewer, so you let him know that you know an optimal solution, which is not always correct. It is a heuristic one. It will be correct in 99.9% of the time, but you need to let him know that you are aware of this. And this is how the brute force approach looks like when we compare the hash values instead of the actual strings. So first of all, I'm going to pick the values of x and modulo. X equals 13, modulo equals 10 to the power of 9 plus 7. Both of them are prime numbers. I'm going to start with an empty array. And what I do next is that I compute the hash value of the pattern string because I need to compare those hash values of the substring to this one. Then I try out each and every substring of length m. So I fix its starting index and I compare if the hash value of this substring, and we are going to see the hash function in a minute, is equal to the pattern hash. Then I just push my starting index to the answer array. And in the end, I'm going to return the answer array. Now let's see how the hash function looks like. In order to compute the hash value of some string s, what I'm going to do is initialize the hash value with 0, and I'm going to iterate through each character s of I, and for that character, I'm going to add to my sum s of I, so the SG code of that character, crossed x to the power of m minus 1 minus I, because this is the number of characters it has on its right. And of course, I take the value of this expression modulo mod, so I make sure that our final value will be modulo mod. In the end, I return the hash value. And this is it. Now let's compute the time complexity of this approach. If I take a look at the main algorithm, what I can see is, of course, here two constant operations. This is also constant. Now this one depends on the time complexity of the hash function, so I don't know yet. Then I have a for loop. Again, this one depends on the time complexity of the hash function. This is constant and this is constant. So we first obviously need to compute the time complexity of the function. If I take a look at the function, I make constant operation here. I return an integer, so also constant here. And what do I do here? Well, I make a total of m iterations in this for loop. So this is m. And this is the tricky part. You might say that this line of code executes in constant time. But this is not true. What happens is that we need to compute x to the power of m minus 1 minus I. You can use a built-in function like pow in C++ or a syntactic sugar in Python, for example. But what happens is that in order to compute this power, behind the scenes, the computer is going to make m minus 1 minus I iterations. So it basically makes a for loop in which it multiplies the answer by x. So don't be tricked by this. In order to compute this value, we actually make m minus I minus 1 iterations. So the actual number of iterations that this line of code will do will be m minus I minus 1. So the time complexity of this line of code depends on the value of I, which is in this for loop. Now what we should do, of course, is take each value of I and add this together. And we will get something like this. For I equals 0, I make m minus 1 iterations. For I equals 1, I make m minus 2 iterations, m minus 3 then, and so on and so forth, until on the last stage, for I equals m minus 1, I make a total of 0 iterations. This is, of course, a Gauss sum, which will be equal to m minus 1 crossed m divided by 2, which is, of course, a time complexity of big O of m squared. So again, don't be tricked by this. the final time complexity of the hash function will be big O of m squared. Now we can get back to our main algorithm and say that this line of code is big O of m squared. And in this piece of code, we make a total of n minus m plus 1 iterations. And for each of them, we call the hash function, which is m squared. So the final time complexity of this piece of code is big O of n minus m crossed m squared, which is definitely greater than m squared. So the final time complexity of the algorithm is big O of n minus m crossed m squared. And as you can see, this is even worse than the time complexity of our initial brute force approach, but don't worry, we are going to make 2 time optimizations, which are going to save us. The first and most obvious bottleneck is computing x to some power, which makes a lot of iterations. So what we can do is actually have all the powers of x that we are going to need pre-computed. As simple as that. We are going to need x to the power of 0, x to the power of 1, x to the power of 2, and so on and so forth. The maximum power of x that we are going to need is x to the power m minus 1. So what I can do is pre-compute all these values and store them into an array, so then I can access these values in constant time. Let's see how the code looks like. Awesome. So all we have to do is first compute the powers of x and store them into the array pow of x, which is going to have a size of m. And then in the hash function, we will just access the value of this element, which will now be constant time. And now the function compute pows, we start with an array, pow of x, which has only one element, which is 1. So pow of x of 0 equals 1, because x to the power of 0, of course, equals 1. And for each and every power, all I do is just push pow of x of I minus 1. So the previous power crossed x, everything modulo mod. Because, of course, x to the power of y can be written as x to the power of I minus 1, everything crossed x, and I make sure that I compute all these powers modulo mod, right? So I write the modulo mod here, so everything is fine. Now, the time complexity of this function, as you can see, is big O of m, because all we do here is a multiplication, and then we just take the remainder. This is constant. We do this for a total of m minus 1 times. So this is big O of m. Here, this is big O of m. And because now this is constant, the final time complexity of the algorithm is going to be big O of n minus m crossed m. So at least we have returned to the initial time complexity. Now, using this hash technique, I'm going to make even one more optimization to make the final time complexity big O of n minus m. The time complexity of this approach is due to the fact that first of all, on stage 1, we try out each and every subarray, and on stage 2, we compute the hash value of each and every subarray. So, big O of n minus m from here, and big O of m from here. What is the one which we can optimize? It is the second one. And why is that? Because we are going to use a technique that we have also used in the arrays chapter, and that technique is based on the fact that we have to compute some information for each and every subarray of some type. In this example, we compute the hash value of each and every subarray of length m. So maybe I can use the fact that I have also computed the hash value of the previous subarrays of length m when I want to compute the hash value of this new one. Let's take an example and see exactly what I mean by that. I've taken again our example. This is the text string and this is the pattern string. And as you can see, m equals 3. So what I'll do is take each and every substring of length 3 and compute its hash value. The first one is text of 0 and 2, which is CAB. So let's write it here, CAB. What is the hash value for CAB? C crossed x squared plus A crossed x plus B. Awesome. Now, when I move to the next substring, which is going to be ABB, what happens is that I remove the first character, which was C, and I add a new character, which is this B, right? So what will happen to this formula? Well, when I remove the C from here, I will also remove this term from the sum. So I only remain with this. And when I try to push another character B, the number of characters on the right of each of these two is going to be increased by 1. So now A instead of being multiplied by x to the power of 1, will be multiplied with x to the power of 2. Now b, instead of being multiplied with x to the power of 0, will be multiplied with x to the power of 1. And then, of course, we add b crossed x to the power of 0, so only b. So what basically happens is that from this formula, I first subtract the first term corresponding to the first character, then I remain with this formula, which I am going to multiply by x. So this is what I get, this one, and then all I have to do is, of course, add my new character, which was b. And I have the hash value of ABB. Let's move to the next substring. The next substring is going to be BBC. So what happens here is that I have to subtract the formula for this character, so I subtract this one. Then with the remaining formula, I have to multiply this by x. So I multiply this by x, and I obtain this 2. And then all I need to do is, of course, add the new value. And I add c. In the general scenario, if my current starting index is I, so I need to compute the hash value of this substring. What I did previously is, of course, computed the hash value of this substring. So one more element to the left, and I don't have this last element on the right. The hash value of the previous substring, which I will denote by hash of I-1, had the following formula. And if I denote the hash value of my current substring by hash of I, it should have the following formula. So as you can see, indeed, the differences between these two formulas is that first of all, we don't have this term anymore. Then all of these are multiplied by a higher power of x. And we also have a new term, which is this one. So we can write a constant relation between hash of I and hash of I-1. It will look like this. And this is indeed way easier to compute. Because I know this value, remember, I've already computed at the previous step, and I know this value is just a character from the string, and I'm gonna know also this value, remember, I pre-compute the powers, then I know this value in constant time, I make the multiplication in constant time, and the addition also in constant time. So computing the hash table of one substring of length m, based on the fact that we already know the hash value of the previous substring, will happen in constant time. And one more thing that I want you to notice here before jumping into the code is that we don't actually need all the powers of x, but the only one that we are going to use is x to the power of m-1. What we are going to do is compute the hash value of the first substring. So compute hash of 0, and this is going to be done by hand. I'm just going to write a for loop to compute this value, and then in order to make the transition to all the other hashes, I'm just going to apply the formula, compare it to the pattern hash, and that's it. Let's see how the code looks like. And this is how the code looks like. Again, I start with x equals 14 modulo 10 to the power of 9 plus 7. My answer is initially empty. I first compute the pattern hash, which is the hash value of the pattern string. We are going to see the function in a minute. Actually, right now, by making this tutorial, I found a smarter way of computing the hash value without even using those pre-computed powers of x, so this is going to be excited. Then I compute using the same function the current hash, which is going to be initially the hash of the first substring from 0 to m-1. If that current hash equals the pattern hash, I make sure to push into the solution the first substring, which starts at position 0, and then I try out each and every substring starting from 1 to n-m, and what I do is compute the new current hash by first subtracting this text of I-1 crossed pow x, and pow x is equal to x to the power of m-1. We are going to also pre-compute it. I'm going to write the code for this later. So after I make the subtraction, all I do is take this expression, multiply it by x, increase it by the new character and everything modulo mod. And of course, if this current hash equals pattern hash, I also push into my answer this starting index. In the end, I just return the answer. So let's see how to implement the hash function in a smarter way, and then how to compute this power of x, and then we will analyze the time complexity. This is the new hash function. I start with the hash value equals 1. Then I take each character in the string s, And what I do is that I just multiply the previous hash value by x, then increase it by the new character c, and take everything modulo mod. In the end, I return the hash value. So what I figured out is that actually when a new character is getting pushed in a string, the hash value is basically multiplied by x and then increased by the SG code of that character. For example, if the string is a, what's going to be the hash value is going to be a. Then if I just push the character b, what's going to be a multiplied now by x and increased by b. Then when I push c, what's going to happen? I multiply all of this by x. So this becomes x squared. This becomes multiplied by x, and then I increase it by c. When I take a d, x to the power of 3, x squared, c crossed x plus d, and so on and so forth. So if we use this formula, we don't even have to pre-compute those powers, which is amazing. And of course, for computing pow x, all you can do is have a for loop in which you are going to multiply x for m-1 times, or you can use a built-in function. It doesn't matter. You do this only once. So even if it takes big O of m to compute, again, being done only once won't affect the total time complexity of the algorithm. So let's analyze the final time complexity. All we do here is two constant operations, constant here. Computing the hash is big O of m. As you can see, I iterate through each character. So these two are big O of m. This check is constant time, pushing is constant time. So this is big O of 1. Then I have a for loop, which does a total of n minus m iterations. And what I do here is, of course, a constant, constant, everything constant inside the for loop. So this is big O of n minus m, this piece of code, big O of n minus m, and returning the answer is at most big O of n, as it might have at most n values, right? So big O of n minus m with all of these is going to get me a total of big O of n. The final time complexity of this algorithm is big O of n. And this is it, guys. Just as a recap, the string matching problem is a fundamental one. It is super easy to be solved using, of course, a brute force approach. Then we can optimize that brute force approach by, instead of comparing the strings, use the Rabin-Karp algorithm and hash each string to an integer using the polynomial formula, for which we have to choose an x, which is going to be prime and can be pretty small, like 13, and the modulo, which is necessary to be a big number. For example, 10 to the power of 9 plus 7, you can use this number. It is pretty safe. It is also a prime number. Remember, we use the modulo because the value of those polynomials are huge. So we need to make sure they fit in the integer type. And this, of course, brings the disadvantage that we might have collisions. Remember, a collision is when two distinct strings share the same hash value, which shouldn't happen because we compare now hash values. And if we see that those hash values are equal, we need to be sure that the strings are also equal. Fortunately, the Rabin-Karp algorithm performs well in real life, but remember, you should have this discussion with the interviewer so he knows that you are aware that the algorithm is indeed a heuristic one. Then what we did is use the classic optimization from the arrays chapter, which was based on the fact that the information for some subarray could be computed faster using the information of other subarrays which we have computed in the past. And the time complexity of this algorithm is a linear one. It is big O of n, where n is the length of the string in which we look for the other string. In the next lesson, we are going to study the Knuth-Morris-Pratt algorithm, which solves the same problem in the same time complexity, so big O of n, but that algorithm is not based on some heuristic, does not have the problem of collisions, and it is preferred over the Rabin-Karp algorithm. So I'll see you there. Bye.